Today, I want to have a look at what I've entitled the course as Wonder in Design. Wonder in Design. The first one I want to have a look at is the wonder in design, color. Color, all right? The wonder of design in color. Now, often it's quite interesting that the simplest things in nature, such as colors, or a bird flying, or a bumblebee, or a flower, very often some of the simplest things that we take for granted and we just look at them and think, wow, that's really beautiful, are actually the most complicated. Now, a great example of this is color. Producing colors. Now, we can produce colors in a number of ways. Paints, we're quite happy to produce color. Dyes, and we can produce with various inks and pigments. And nature, in fact, does use biological pigments to produce color. We call them these biochromes. So nature produces colors, biological pigments called biochromes. But nature has another way of producing color. And this color we call structural color. Structural color is color that harnesses the physics of light at a nano scale. So what actually happens in nature is that nature is able to produce colors by actually creating physical objects that cause the light to actually bounce off them and to create color from that and that's actually, and it does it by refraction, it does it by diffraction, and it does it by interference. Now, the amazing thing about these colors is that they're used in peacock feathers, they're used in butterflies, particularly the blue morpho butterfly we'll talk about, and they're used in the cotinga bird, the colors that come of these. Now, what's unusual about these colors is that if you had to look at these colors, they are really, really vivid, really, really bright, far more so than colors that you would normally create with paints or with pigments. These colors literally pop, all right? So obviously science has been very interested about how we can produce these type of colors. How does nature do it? And in fact, the reason that they're wanting to do it is that colors that are structural colors never, ever fade. Can you imagine having colors that never, ever faded on your house, ever? Pigment colors, paints, all go faded with light and that. Structural colors never fade. You can look at a structural color for 1,000 years ago and it still is bright and as perfect as it was then. Structural colors are non-toxic. They're in fact edible. Okay, the reason they're edible is because they're actually not pigments. They're colors that are created from physical structures, so you can actually eat them. They're completely non-toxic. Thirdly, these structural colors are 10 times, more intensive and brighter than any color you can produce with pigments. They have huge contrast ratios, all right? Vivid, deep blacks and brilliant, brilliant whites. And they're really easy to change or to add colors to. So let's just talk a little bit about inference structures. And I want to concentrate on the morpho butterfly. Now, you've all looked at a butterfly, and I don't know if we have morpho butterflies here. I know that they're, I think, probably in the Amazon jungle and those sort of places. But the morpho butterfly has a really intense blue-wing color. And it's the consequence of these color-producing structures. And what actually happens with the morpho butterfly is the following. Is that if you were to zoom in on the morpho butterfly wing, you'd see that it comprises, there's the wing there. You'll see that it's got, if you were to zoom in, you would see a number of scales on the wing. If you were to zoom into that little area of the scale, you would see that what actually happens is that you get these layers with air in between. And if you were to zoom in on one of those layers, you would actually find that there's a whole lot of these structures here that are almost like trees on the wings. Little tiny trees with branches sticking out. All right? There's actually a photograph from an electron microscope of one of these close-ups of these structures on the wing. And you can see, in fact, that we've got all of these little trees with branches sticking out of them. Can you see them all there, resting on there? Now, to give you an idea of the size we're talking about, that size there is 1 nanometer from there to there. You say to me, well, what's a nanometer? Well, if I were to take a piece of paper, presumably one of these, that piece of paper, that edge, is probably in excess of 100,000 nanometers in thickness. And each of these scales of the butterfly, all right, each of these scales is composed of an upper and lower lamina, which are separated by a void, held up by vertical rods. All right, you can see these vertical rods here. These laminae support all of these tree-like structures with their branches projecting from a central stalk. Now, you might say, well, how on earth do this produce color? Let's talk about constructive and destructive interference colors. If I get a wave like that, and I get another wave, okay, and the waves line up so that the two valleys meet and the two troughs meet, what will happen when I combine the two waves? You'll get a bigger wave, right? The two valleys go together and hit together, and the two waves form. So you'll actually get a wave with a higher peak and a higher valley. That is called constructive interference. If you have two waves running together, but they're in exactly opposite, so in other words, a trough of one wave hits the valley of another wave, and they were to crash together, what would actually happen? They'd cancel each other out. Essentially, the trough and the valley would meet, and they'd cancel each other out. And if the waves were identical in height, you would get a flat line, essentially. So that's what we call destructive interference. So what actually happens in amorphous butterfly wings is that the light comes, it hits the branch, and it reflects back, a full wave. All right? What actually happens is that the next wave comes and hits the next branch. Because there's exactly half a wavelength of blue light between the two, it does half a wavelength and then half a wavelength back off the bounce to exactly match the wave that hit the tree, the branch above it. So it creates constructive interference. The third wave comes down, hits the third branch, is exactly half a wavelength traveling that way and half a wavelength traveling that way, which means that it also has constructive interference with the wave above it. So when you have 6 or 7 of these branches, you end up essentially with all of these waves of exactly blue light, because it's only half, it's the exact distance for the wavelength of blue light only. So it basically takes this beam of white light, all of the blue light gets bounced back exactly off 8 or 9 of these branches and combined into one vivid, bright blue beam, because it creates a constructive interference wave of 8 or 9 of these branches. Can you see that? What happens to all the other light? Well, the other light essentially gets absorbed by pigments on the bottom of the scales, soaks up a lot of the reds and all the other colors, and most of the other colors, because they're not being constructively interfered, they are destructively interfered, they cancel each other out. So you don't see any of the other colors, they just cancel each other out. The waves just crash together and a much lower amplitude. A couple of things then. Simple things are not often simple. Number one, we realize that in order to work on amorphous butterfly's wings, the following must occur. The distances between the branches must be exactly half the wavelength of blue light to produce the color. The height of the rows of the tree-like structures must be irregular in order to produce a diffuse and uniformly blue color with a wide viewing angle. Thirdly, the number of layers of branches on each tree must be between 6 and 10 layers in order to produce the brightness of the color. And fourthly, each scale holding the trees must have a pigment beneath them in order to absorb unnecessary green to red light, which reduces the background reflection and enhances the blue structural color. Similarly, structural coloration is done in the peacock's tail feathers. The peacock is an absolutely phenomenal bird. The peacock tail feathers are just stunning, absolutely stunning. Darwin got real frustrated with peacocks. He didn't even want to look at them because they really put a bit of a bit of a poison in the well for evolution, because they're really difficult to explain why a peacock would even evolve feathers like that. I mean, does that look like survival of the fittest to you, carrying that lot around? And the worst is they're not actually necessary for sexual reproduction, which is the whole purpose of evolution. They've actually proved that. Female birds aren't that impressed with the big tail feathers. Okay? So the reason I wanted to show you the peacock tail feathers is that they do the same thing. Bright colors of the peacock tail are caused by structural interference. The colors produced by the structure of the feather barbules. Each barbule is 60 nanometers wide, 5 nanometers thick, with layers of keratin on each side, 0.4 nanometers thick. Similarly, structural coloration is done in the peacock's tail feathers. The peacock is an absolutely phenomenal bird. The peacock tail feathers are just stunning, absolutely stunning. Darwin got real frustrated with peacocks. He didn't even want to look at them because they really put a bit of a bit of a poison in the well for evolution, because they're really difficult to explain why a peacock would even evolve feathers like that. I mean, does that look like survival of the fittest to you, carrying that lot around? And the worst is they're not actually necessary for sexual reproduction, which is the whole purpose of evolution. They've actually proved that. Female birds aren't that impressed with the big tail feathers. Okay? So the reason I wanted to show you the peacock tail feathers is that they do the same thing. Bright colors of the peacock tail are caused by structural interference. The colors produced by the structure of the feather barbules. Each barbule is 60 nanometers wide, 5 nanometers thick, with layers of keratin on each side, 0.4 nanometers thick. That is really not thick. It's thin. It is so inconceivably tiny, all right? Just right. 0.4 nanometers is exactly right to cause interference when the light reflects off them. The patterns are digital patterns that combine the effects of thousands upon thousands of individual barbels, perfectly coordinated with every single one to get that color. Otherwise, you would just get a total mishmash. Every single one of those barbules has to be perfectly coordinated with the next to produce that light. But even more amazing in a peacock's feather is you'll notice that the feather has got distinct borders between these colors. When you consider that these colors are only produced by light bouncing off barbules, how do you produce a sharp border between black and green, or between green and gold, when all you're doing is bouncing color off something? It effectively means that the boundaries between the colors to be sharp, the feather barbules must be programmed to abruptly increase or decrease their thickness at precisely the right places and in precisely the right angles in order to get the borders of those colors. A quote from Professor Stuart Burgess, Professor of Engineering Design at the University of Bristol. He says, "The peacock tail feather has beautiful iridescent colors produced by thin film interference. The feather has layers of keratin with precision thicknesses comparable to the wavelengths of the individual colors of white light. The feather barbs are incredibly well aligned to produce mathematical patterns like ellipsoids and cardioids. The design of peacock feathers is so precise that engineers cannot replicate it. Yet the feathers seem to exist purely for decoration. I think that the peacock feather shows not only is there a creator, but that creator is extremely wise and very caring." Kenny Sin, "I will shout joyfully about the works of your hands, O Lord. Wonder and design, Kenny Sin." Now, if you talk about Kenny Sin, Darwin, when he was putting together his theory of evolution, the paradigm of the day was that simple things are simple, and that simple things are basically things like cells and so forth, are just contain a few of your basic ingredients. All right? So the idea was that simple cells were simple, and the original cells that first started were probably just a few simple proteins and a few simple amino acids and a few simple this and that. And basically what actually happened is that today we talk about our last universal common ancestor, LUCA. And you'll hear scientists talk about the last common ancestor. What basically that means is that cell from which all life was supposed to have originated. And they assume that that's going to be a really simple cell, pretty much like that. But as time has progressed and we've managed to look more and more at cells and start to see the complexity of cells, we've actually started to find out that actually they're not that simple. They're pretty complicated. And as we've started to get more and more powerful microscopes and so forth, we've actually found out that, in fact, a cell is really, really complicated. And recently, with the latest developments in our ability to look at life and to cells, we've got the oh my God moment when they've looked at these cells and they've realized that every single cell in your body is an entire world containing thousands upon thousands of components that are all working together like a little miniature planet with thousands of little manufacturing things going on inside of your cells. Simple cell, not so simple. Really where I'm going to go on about is I want to talk about kinesin. Now, if we talk about a cell, within a cell, we have got thousands upon thousands upon thousands of highways in every one of the living cells in your body. Did you know that? You've got highways in there, roadways. These roadways are microtubules, and they're actually 10 nanometers in diameter. So these microtubules actually form an intricate set of pathways or roadways in a cell. See the cell there is the nucleus of the cell? See all the pathways, all the highways, superhighways, thousands upon thousands of them, all in your cell. These roadways or these microtubules are actually highways that allow nutrients and proteins and all of the things that you need to survive to be transported along. How do you think your body and all the cells in your body and all the bits of your body get what you need? We kind of think, oh, the blood takes it to them. Well, actually, what happens at a smaller scale than that? And I just want to just show you this. These are the microtubules through an electron microscope in one of your cells. And I've just expanded them for you. And I've actually got a drawing there of a microtubule. Now, the reason that I want to talk about kinesin is kinesin are postmen. In every one of your cells of your body, you have got hundreds and hundreds of thousands of postmen. These postmen deliver all of the nutrients that every one of your organs and cells require. They have got arms, 2 arms, and they carry stuff with the 2 arms. They have got 2 legs. They walk along these microtubules. They take an 8 nanometer step every step they talk. 8 nanometers, 8 nanometers, 8 nanometers, 8 nanometers. They're walking right now along the highways in your body. Little men, little postmen. They are 7.5 nanometers long. That is 3 millionths of an inch, or 70 billionths of a meter. All right? They are 15 times more powerful than a man-made engine in terms of efficiency. All right? They're capable of 100 steps per second. That's equivalent to you and I moving at 600 meters per second. It's pretty impressive. You've got little postmen going on your highways at 600 meters per second right now in your body. Millions of them. Taking stuff around. How cool is that? They've got little arms. They've got little legs. All right? They can go into sleep mode. They can do all sorts of cool things. They've got a handover mechanism. If they get tired or they've got something that's too heavy for them, they give it to somebody else. Hand over. They've got a bypass mode ability. If they're walking along a highway and something's in the way or something's broken, they've got a GPS tracking system that actually lets them reroute and find their way to where they need to go. How amazing is that? They've got a sleep mode to save energy. If they're not needed, why waste energy? They go to sleep. They're powered by ATP, and we'll talk about ATP in the evolution when we talk about the ATP. And they're team players. They help one another. If a load's too heavy, other people come and they share the load together and they walk together. They're recyclable. Once one isn't needed anymore, if you've got too many, they're actually recycled into useful stuff that somebody else can use.
Inside a living cell is an amazing transportation system. Proteins have to be delivered to the correct part of the cell to perform their intended functions. This animation, based on a lot of clever research over a number of years, shows how it happens. Highways made of microtubules are assembled by interlocking proteins, each manufactured in accordance with the coded instructions on the cell's DNA. Marching along a microtubule is the kinesin motor, the hero of our story, carrying a huge sack of proteins to be delivered to a predetermined place in the cell. Here, the proteins will be released to fulfill their functions. A kinesin linear motor uses 1 ATP to provide the energy for each step and takes 125,000 steps to cover 1 millimeter. This amazing machine shows all the hallmarks of design.
Our results show that a molecular motor must take on a large number of functions over and above simple transport if it wants to operate successfully in a cell. It must be possible to switch the motor on and off. It must be able to accept a load needed at a specific location and hand it over at the destination. It is impressive how nature manages to combine all of these functions in one molecule. In this respect, it is still far superior to all the efforts of modern nanotechnology and serves as a great example to us all. When you're a postman, you need to know where to go to pick up your post, yes? You need to have somebody give you the stuff and put a label on it so that you know where it's going to go to. You need to be able to hold it. You need to be able to walk. You need to have a highway that takes you there. You need to be able to overcome any obstacles on the way. When you get to your destination, you need to be able to check the address on your package, matches the address, and you need to be able to hand it to someone who needs to be able to take it from you. All of that happens, of course, all by accident, in your body all the time. The wonder of design in mathematics. Now, I see a lot of stuff in creation that I get excited about. Morpho butterfly wings, peacock tails, all of this stuff is pretty cool, especially if you understand that the most simple things are sometimes the most complex. All right? It's always true. To get something really simple to function really well, that's why Apple did so well in its iPhones and so forth. Everybody else really went for all of this complicated stuff and buttons, and there was just all sorts of stuff. Apple somehow made it simple. You could just touch stuff, and it was just laid out so simple. But belying that simplicity was incredible complexity, but it wasn't right in your face. It was beneath the surface. And that's why it worked. That's why everybody intuitively knows how to use an iPad. My little 1-year-old granddaughter knows how to use an iPad really well. Trust me, she's got Suri doing all sorts of stuff, you know. She's great at it because it just works, because it's so simple. But beneath that, there's incredible complexity. Mathematics does that for me. I'm not by any stretch of the imagination a mathematician, but I can appreciate maths. Mathematics is the language of life, of physics. Everything you see around you, everything is running off mathematics. God is the consummate mathematician. Have a look at some of these quotes. Leon Lederman, physicists defer only to mathematicians, and the mathematicians defer only to God. Isn't that beautiful? Galileo, mathematics is the language in which God has written the universe. I want you to understand something about maths. Mathematics is not something that we invented, all right? Mathematics was discovered. It was not invented. Mathematicians did not invent math, they discovered it. Ancient mathematicians didn't invent addition, they just discovered it. Pythagoras, who remembers him? The square on the hypotenuse is equal to the sum of the square of the other two sides. Hey, we had it all drummed into us, and we all know Pythagoras' theorem. One of the most important theorems in the history of mankind, incidentally. That little theorem belies a tremendous amount of sophistication. He didn't invent his theorem. You know, he didn't just sort of You can sort of imagine Pythagoras kind of going along with the right angle triangle and suddenly discovering that, a squared plus b squared equals c squared, and going, wow, that's really cool. He didn't decide that. He discovered something that was there. And what was really cool is that no matter how weirdly shaped his triangle was, or what size it was, providing it had a right angle in it, that were true, always. Wow, that's really weird. I wonder where that came from. So mathematics is built into the universe. So I want to just look at a couple of quick examples of maths in the universe, and I'm hoping you get excited about them. The first one I want to talk about is Euler's identity. All right. Here we go, guys. Hold on to the seats. All right. Euler's identity. All right. If I were going to have a party for numbers, America's Got Talent, I'm going to invite the most important numbers in the entire universe to my party, I would invite 0. Okay? Zero's a really important number in maths, okay? The concept of 0, I can't even go into it, but it is absolutely mind-staggering what the concept of 0 actually means to us, okay? If we didn't have 0, we'd be pretty stuffed, all right? The concept of 0. So definitely I'm going to invite 0. I would also invite 1. 1's really important. Without 1, you pretty much only got 0, right? So the concept of unity, really important. The concept of 0 and 1 are foundational to all your maths, okay? They are the fundamental numbers of arithmetic from which all integers can be derived. 1828, blah, 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 blah. Don't worry about Euler's number. I can't go into it. I'm not trying to blow you away with it, but essentially it has to do with logarithms, and it comes from the equations for compound interest. It's an absolutely to die for important number in maths. In addition to that, I would invite pi. Let's be honest. What's a party without pi, right? You've got to have pi. And I would have to bring along as my last guest of honor, okay? I would have to bring along the imaginary number, I. Without I, you are seriously not going to get anywhere in maths. It's the square root of a negative number. The important thing about these numbers is all of these numbers are embedded in the universe. We didn't invent them. We invented the symbols, but the principles that these numbers represent, noughts and ones and Euler's numbers, and the fact that a circle's circumference divided by a diameter, all of those things are things that we discovered. We're like, wow, that's really cool. Okay? But what's interesting about these 5 guests is they are completely independent from one another. Euler's number has got absolutely no interest in the diameter of a circle. Did you know that? And pi has got little interest in logarithmics or in negative roots. And 0, quite frankly, is bored with a whole lot of them. If you take e and raise it to the exponent pi I, and you add it to 1, you get it equal to 0. Now, if you're a mathematician here right now, you should have the hair on your back of your neck standing straight up. And like me, I got goosies. I mean, I could stare at that equation for hours, okay? I know people that have had it tattooed on their arms, okay? Okay? This is a big deal, guys. If you don't get it, I can't make you get it. But this is absolutely mind-blowingly, gobsmackingly OMG. How is that even possible? You know what I'm saying? You have Harvard mathematician Benjamin Pierce saying, that is surely true. It is absolutely paradoxical. We cannot understand it, we don't know what it means, but we have proved it, and therefore we know it must be truth. Guys get so excited about this that they actually say that it's the equation that governs the whole universe and even defines the human soul, the God equation. This equation was voted the sexiest, the most beautiful, the most gobsmackingly unbelievable, oh my God equation of all equations. People look at this equation and they just go, I just love this equation. So if you're not feeling it, you're not mathematicians, all right? If you're feeling it, if the hair's standing up on the back of your neck and you got goosies, welcome to the club, all right? It combines, okay, it combines 5 of the most important numbers in the entire universe that are completely unrelated to one another into a single equation. In addition, 3 of the most important of the 5 operators, addition, multiplication, and explanation, are brought into this equation. And the concept of unity and the concept of 0. And they all equal exactly 0. How is that even possible? Why is that equation coming out exactly to that? Not 1.65, not 9.92, not 7.627352, but 0. It is just unfreaking believable. All right. I want to talk about the Fibonacci sequence and the golden ratio really quickly. The Fibonacci sequence and the golden ratio. The Fibonacci series gets its name from Leonardo Fibonacci, who lived in the 12th century. What he actually was trying to do is he was trying to calculate the ideal expansion of pairs of rabbits over a year. So that's what he was actually trying to do. These rabbits are going to mate, and they're going to have kids, and they're going to mate. And he was trying to work out kind of like how many rabbits he'd end up with and how long it would take him before we'd all be overrun by rabbits. So it kind of started off like that. Essentially what he did in order to work out these rabbits is he took a number and he added the 2 numbers before that number to get the next number, and then he would add the 2 numbers before that number to get the next number. So he ended up creating this sequence. So he would take 0 and 1 to get 1. He would then add 1 to 1 to get 2. And then he would add 2 plus 1, the previous 2 numbers together to get 3. And then he would add 3 plus 2 to get 5. And then he would add 5 plus 3 to get 8. And then he would add 8 plus 5 to get 13. And so on. And so he produced a sequence of numbers, 0, 1, 1, 2, 3, 5, 8, 13, etc. All right? Now, this particular sequence of numbers is really an interesting sequence of numbers. I tell you why it is because nature uses the Fibonacci sequence absolutely everywhere. Absolutely everywhere. They are nature's numbering system. They appear everywhere in nature, from leaf arrangements in plants to the pattern of florets in a flower, the bracts of a pine cone, or the scales of a pineapple. The Fibonacci numbers are applicable to the growth of every living thing, including your cells, grains of wheat, beehives, and the whole of mankind. All right, and if we would have a look, you'll see that these sequences actually appear in flower petals, all of these things, right down to your DNA and even to black holes. And you can see there, if you look at the branches or the leaves and branches of trees, they follow that exact sequence. All right? The fingers on your hand, all of these things follow that numbering sequence. Why should they? I mean, really, if nature is just blind chance and forces that are undirected, why would it follow a particular sequence of numbers? I mean, it's kind of hard work, especially if nature didn't like maths, right? 0, 1, 1, 2, 3, 5, 13. Why are we following that sequence? Now, perhaps even more amazing, is that this particular sequence is actually used to produce what we call the golden ratio. The golden ratio, 1.618033, is actually all over nature and all over art today. Mathematicians and artists took each number in that Fibonacci sequence and they divided it by the previous number. So what actually you end up with is the following. 1 divided by 1 is 1. 2 divided by 1 is 2. 3 divided by 2 is 1.5. 5 divided by 3 is 1.66. 8 divided by 5 is 1.6. 13 by 8 is 1.625. 21 by 13 is 1.615. And eventually, if you were to carry on doing that, you would get closer and closer and closer and closer and closer, but never ever exactly reaching, 1.618. All right? Exponential, going on and on and on and on. So this particular number is actually called the golden ratio. So what actually happens here is the following. The Greeks love this, by the way, is that the important thing about this is that if you were to create a square that was exactly 1 by 1.168, you would get what is called the golden rectangle. So you can see that for every one of these rectangles, if I were to take away the 2, I would get the 1s, that rectangle there. If I were to take away the 3, I would get that rectangle there. If I were to take away the 5, I would get that rectangle. If I were to take away the 8, I would get that rectangle. It is an embedded exact quantity of rectangles, exact proportion within every single other rectangle. You understand what's happening there? So that particular sequence, now if you were to take that sequence and you were to, in fact, do exactly what they've done there, build up the sequence in the Fibonacci sequence of those rectangles, and you were to draw a line through the center of every one of those squares, you would end up with that spiral. See the spiral there? Going through exactly those numbers. 1, 2, 3, 5, 8, 13, 21, 34. That particular sequence of numbers is everywhere in nature, and it's everywhere in architecture. It's actually being used in the Parthenon in Athens. It's used in the Mona Lisa. It's used in the Eiffel Tower. It's used in many, it's the exact proportion that's supposed to be pleasing to the eye, restful to the soul, and nature likes it and uses it everywhere. Nobody can explain why these numbers and these sequences appear absolutely everywhere in Mother Nature. I'm going to show you a quick video now that'll probably do it better than I did. Design biomimicry. He's before all things, and in him all things hold together. Colossians 1:17. Biomimicry is an approach to innovation that seeks sustainable solutions to human challenges by emulating nature's time-tested patterns and strategies. Biomimicry is us geniuses with all of our brains and all of our research and all of our tools unable to produce anything better than nature. So what we're going to do, we're going to look at the test paper and copy her. All right? It's the only way we can get there. So we look at nature and we see her as the perfect example of what things should be. I quote Janie Benyas, who's the co-founder of Biomimicry Institute. Biomimicry is innovation inspired by nature. Engineers, architects, and other innovators are nature's apprentices. They are driven by the question, what if every time I started to invent something I asked, how would nature solve this problem? All right, so before you create something, ask yourself, how would nature solve this problem? The reason that we want to copy nature are the following. Incidentally, that's a great picture of a hawk and biomimicry in action there, where we've emulated that with a modern aircraft. All right. The reason we copy biomimicry is nature runs on sunlight. How cool is that? We don't have to have gasoline. We don't have to have all of this stuff. Nature runs on sunlight. Great. Nature uses only the energy it needs. No waste. Nature fits form to function. Nature recycles absolutely everything. Nature rewards cooperation. Nature banks on diversity. Nature demands local expertise. Nature curbs excesses from within. And nature taps the power of limits. Nature has got some really interesting things that it does. In addition to all of these things, nature doesn't ever create something and then kind of it just does one thing. A good example is the elephant's trunk. I mean, have a look at the elephant's trunk. We're trying to copy it today. The elephant's trunk, do you know that an elephant's trunk can actually pick up a log, a massive log, okay, with its trunk and its tusks? But it can uncork a champagne bottle and it can pick up a pin. Did you know that an elephant can pick up a pin with its trunk? Absolutely phenomenal appendage. And they've spent some time now trying to just work out how that thing works and see if we can try and copy it. All right? A typical example of biomimicry. We can't even come close to emulating what a trunk. We might be able to get it to kind of move around and grab an apple. Okay, but that's about it. But have a look at what nature has done with this trunk. It smells. It drinks. It drinks through it. It smells through it. It touches. It hears. It feels. It communicates. It snorkels. It defends. It can do all of these things in one appendage. That's pretty cool. All right? I'll just go through a couple of quick ones, and then I've got a video that actually does it better than I could ever do it. So a couple of good ones. The kingfisher beak was the inspiration for Japan's bullet train. The nose was exactly modeled on that. What was actually happening is that this train travels at over 200 miles an hour. It was really cool until it hit a tunnel. And every time it came out of the tunnel, okay, it caused a massive change in air pressure that caused thunder sounds that you could hear over a quarter of a mile away. So every time your train shot out of the tunnel, you'd just get this massive sonic boom, and everybody would be like, ah, and it would just be heard for miles around. So yeah, they looked at the kingfisher beak, how it empties the water, and they modeled the nose on that. Solved, problem solved. In fact, the resulting design was based on the narrow profile of a kingfisher's beak, resulting in a much quieter train, consumes 15% less electricity, and goes 10% faster than before. Gecko feet, adhesives. Amazing adhesives coming off the gecko feet. The team at University of Massachusetts developed a gecko skin, an adhesive so strong that an index card size strip can hold up to 700 pounds. Okay? Based on gecko feet. The shark swimsuit. We all remember the farce that happened during the Olympics, where they actually had to ban the suit, okay, because they were so efficient. All right, so modeled again off shark skin, where a shark skin is made up of countless overlapping scales called dermal denticles, little skin teeth. These have grooves running down their length in alignment with the water flow. The grooves disrupt the formation of eddies or turbulent swirls in the slower water, making the water pass by a lot faster. It discourages also growth on the skin. So Really cool stuff. This one here I came across recently. These particular beetles, actually in the desert, actually put themselves in this particular position, and the desert fog condenses on their bodies, and it actually runs down into their mouths. So they've actually developed the dew bank now, which does the same thing. With a little cap there, it catches the water, and you can actually drink water. All right? Mercedes-Benz modeled the car on the aerodynamics of the boxfish. They actually worked out that it's got the aerodynamically superb and one of the most efficient shapes of any car of its size. All right. Famous one we all know is Velcro. Velcro was actually developed from a Swiss engineer who discovered the burrs on animals and saw how they stick, and that's actually been developed. And of course, we understand Velcro.
I'm not trying to replicate biological systems. I'm interested in their function. When I watch the cheetah run, I can see a lot of details. I can see the muscle getting tense, and then at the end of the stroke, you can see the paws flicking and then darts are flying. And I can see energy exploding from this biological machine. That's really fascinating. We can study why the cheetah is the fastest land animal, and we can extract the design principles. Those principles we can actually implement robotics. Here at MIT, we aim to achieve a fast, agile, and energy-efficient robotic cheetah that can be used in the field.
I had to have a giggle when I saw his cheetah. And I was just thinking, man, you seriously are behind the curveball in terms of that. Did you guys feel that as well? It just looks so clunky, didn't it, in comparison with the beauty of that cheetah. So that's biomimicry. Intelligent people with instruments are still unable to produce what supposedly Mother Nature did purely by accident. And we're having to copy them, and we're nowhere near being able to generate things at the efficiency and the beauty and the elegancy and the simplicity and the cleanliness and the recyclableness and the functionality that these things are able to do. Interdependency, the wonder of design and interdependency, and I'll finish off there. If you talk about a complex system in nature, a complex system has more than one part in it. It's like a watch. And in fact, I think I've got an illustration of a watch somewhere. Okay, I'm going to skip Darwin for a minute. We've got a watch. And if you have a look at a watch, a complex system, you'll see that in order to provide the functionality of a watch, which is essentially to tell you the time, it has a whole lot of different components. And you'll notice that every one of those components needs to work together. All right, if you've got a cog spinning round and it's not interlacing perfectly with another cog, you're not going to have something working. So things need to work together interdependency upon one another. We happy with that? All right, so the whole concept of interdependency is very, very critical. And it's something that I've often thought about. Here's the argument logic. Complex systems must integrate their individual parts to achieve their function. Yes? Right. Integration of individual parts to function requires foreknowledge of a designer. Would you agree? If I'm wanting to tell the time and I'm putting together individual parts, I have to know what the end game is in order for those parts to be putting together. Otherwise, why would I be putting that to that if I didn't know what the end game is? So you require the foreknowledge of what the final function is going to be. Very critical to realize that evolution is blind, has no foreknowledge. It simply does things without knowing the end game, which to me is you'll never ever arrive at anything. So thirdly, therefore, complex systems require a designer. The concept I want to introduce to you is what I want to call irreducible complexity. Okay, irreducible complexity is the following. It's basically saying that in order for a watch, and all of these pieces in a watch to function, you need to have them all working together with each other to achieve the purpose of the watch, to tell the time. You can take some of the pieces away from the watch. All right? Maybe the watch strap. If I took it away, what would happen? Still have a watch, right? You can take pieces away, but you reach a point where if you take any more pieces out of the watch, the thing ain't going to work anymore. Agreed? And that has been illustrated by a guy called Michael Behe. And he's actually been a big advocate for intelligent design. And this was one of the strongest arguments. And if you're an apologist, you need to know about irreducible complexity. It's the hot topic out there at the moment, okay? Along with pretty much everything else I've talked about tonight. Bacterial flagellum. So has a bacterial flagellum evolved step by step? And at what point is it irreducibly complex? I want you to understand that a flagellum has this tail. See this tail here? This tail is actually driven, there's the tail there, by a motor. The motor has a C-ring and studs and a stator, S-ring and M-ring, a rotor, has an inner and outer membranes. It has a hook, a universal joint, has a propeller, it has bushes, it has a clutch mechanism. All of these things are actually built into this device. Now, I'm not imagining this, and I'm not making this up. This is not an actual photograph, but this is a drawing of the actual flagellum motor. So these little flagellum and the bacteria spin these little tails around exactly like that. These little tails are pretty phenomenal. Self-assembly and repair. Okay? Water-cooled rotary engine drives the tail. It's a proton motor force drive system powered by protons. Forward and reverse gears. How cool is that? Operating speeds up to 100,000 RPM. Direction reversing capacity or capability within a quarter of a turn. These things can literally turn on a dime. Hardwired signal transduction system with short-term memory. So this bacterial flagellum is an absolutely amazing piece of machinery. I'm going to show you a quick video that lasts about 4 minutes. And basically, they actually put the following question to you. Here you've got a bacterial flagellum with a propeller driven by a motor. It needs these things to move around. We're asking the question, how did this thing evolve step by step? Okay? How does a motor evolve step by step? How does the tail know that it's going to need a rotor? And the rotor know that it's going to need a propeller. And the propeller know that it's going to need a clutch. These things are all supposedly evolving independently. You understand what I'm saying? So I'll show you quickly the movie on this, and then it'll explain it probably better than I. Everyone all right?
For the longest time, I believed that Darwinian evolution explains what we saw in biology. Not because I saw how it could actually explain it, but because I was told that it did explain it. In schools, I was taught Darwinian biology.
One machine particularly attracted his attention.
I remember the first time I looked in a biochemistry textbook and I saw a drawing of something called a bacterial flagellum with all of its parts in all of its glory. It had a propeller and the hook region and the drive shaft and the motor and so on. I looked at that and I said, that's an outboard motor. That's designed, that's no chance assemblage of parts.
Behe's reaction was not surprising, for the molecular motors that drive bacteria through liquid each depend upon a system of intricately arranged mechanical parts. These parts come into focus when portions of a cell are magnified 50,000 times. Biochemists have used electron micrographs like this one to identify the parts and three-dimensional structure of the flagellar motor. In the process, they have revealed a marvel of engineering on a miniaturized scale.
Howard Berg at Harvard has labeled it the most efficient machine in the universe. These machines, some of them are running at 100,000 RPMs. and are hardwired into a signal transduction or sensory mechanism so that it's getting feedback from the environment.
And even though they're spinning that fast, they can stop on a dime. It only takes a quarter turn for them to stop and shift directions and start spinning 100,000 RPM in the other direction.
And just like outboard motors on motorboats, it has a large number of parts which are necessary for the motor to work.
The bacterial flagellum, 2 gears, forward and reverse, water-cooled, proton motive force. It has a stator, it has a rotor, it has a U-joint, it has a drive shaft, it has a propeller, and they function as these parts of machines. It's not convenient that we give them these names. That's truly their function.
Since its discovery, scientists have tried to understand how a rotary motor could have arisen through natural selection.
All told, there are about 40 different protein parts which are necessary for this machine to work. And if any of those parts are missing, then either you get a flagellum that doesn't work because it's missing the hook or it's missing the drive shaft or whatever, or it doesn't even get built within the cell.
In evolutionary terms, you have to be able to explain how you can build this system gradually when there's no function until you have all those parts in place.
But could Darwin's small, favorable variations have produced a bacterial flagellum? Some scientists doubt the possibility.
How could something new, like a bacterioflagellar motor and all of the components that go with it, how could it develop out of a population of bacteria that don't have that system? When each change, according to Darwin's theory, has to provide some kind of advantage.
Some scientists praised Behe's work, while others dismissed it as unscientific and religiously motivated. Behe's critics also insisted that he had underestimated the power of natural selection. They argued that the flagellar motor could have been constructed from parts used to build simpler molecular machines, like this needle-nose cellular pump. If the components of the pump already existed, they could have been preserved by natural selection even before the bacterial motor arose. This theory is called co-option.
It's essentially saying that evolution or natural selection at some point was able to borrow components of one molecular machine and build a new machine with some of these components.
Scott Minnick has studied the flagellar motor for nearly 20 years. His research has led him to challenge the co-option argument.
With a bacterial flagellum, you're talking about a machine that's got 40 structural parts. Yes, we find 10 of them are involved in another molecular machine, but the other 30 are unique. So where are you going to borrow them from? Eventually, you're going to have to account for the function of every single part as originally having some other purpose. So you can only follow that argument so far until you run into the problem of you're borrowing parts from nothing. But even if you concede that you have all the parts necessary to build one of these machines, that's only part of the problem. Maybe even more complex, I think more complex, is the assembly instructions. That is never addressed by opponents of the irreducible complexity argument.
Can you imagine a bacterial flagellum that has got this long tail sticking out the back that doesn't do anything? It doesn't spin because the motor hasn't evolved yet, the parts aren't in place. Do you see that as a survival of the first evolutionary advantage? I don't think so. So we're saying that basically, in order for the motor to work, you would have had to have a bare minimum number of parts to make it irreducibly complex, to be there at the same time and all working together in order for to perform the function of movement. And they talked a little bit about the co-option theory, which is the most common reply that atheists have to it, and it's just not a valid option. Dawkins, our beloved friend, wrote a book in reply to the watchmaker argument that we spoke about earlier, and basically said that nature is full of bad designs. Therefore, if there is a watchmaker, he's blind. And he wrote the book, The Blind Watchmaker, which he's quite familiar with. And basically he says that everything in nature gives the appearance of having been designed, but there's so many examples of bad designs, there can't be a God. And the argument basically is that the teleological argument, or the argument from poor design, and it basically goes like this. An omnipotent, omniscient creator God would create organisms that have optimal design. All right? He says organisms have features that are suboptimal. Therefore, God either did not create these organisms, or he is not omnipresent, or omniscient or omnipotent. All right? And that's the argument. And he presents in his book many examples of what he considers to be poor design. I mean, we've all heard about the vestigial organs. We've heard about appendixes and tonsils and all of these things that for many, many years, even while I was a child, we were taught that these were leftovers from evolution and that they served no purpose. And when I was a kid, whooping out tonsils was pretty much like eating lollies. Yeah, standard. What has science discovered? How arrogant we are to think that we actually assume that something's there for no purpose, and suddenly we discover, oopsie doodle, actually they have a function. But he basically criticizes the inverted retina in the eye. It's his big one that he uses, and he basically says that the eye and the design of the eye is a complete tax-up, all right? The light that comes into your eye has to go through a bunch of cables before it hits the retina. Talk about poor design. If there's a God, the dude seriously wasn't thinking straight when he designed the eye, and he's probably blind. And that's his whole argument. And actually, it's been an interesting argument because the eye actually appears to have been designed incorrectly. It's actually designed backwards, and the light has to go through all of this stuff to get, it doesn't make sense. Until fairly recently, a bunch of scientists in Israel actually went ahead and studied the eye in detail. And I haven't got a lot to say about this, but basically you'll see different magazines there. I've got the Science Daily and different ones there. Mystery of the reverse eyeball has been solved. Backward wiring of the eye retina confirmed as optimal. They've actually done studies on it. They've worked out that this is an absolutely exquisite design, and that if it were designed any other way, you would not be able to see as well as you do. All right? And there's a whole lot of stuff around that, and you're welcome to look at news releases. The other big one that everyone goes on is, of course, junk DNA. Most of our DNA is junk. It's left over from evolution, and we don't need it anymore. Of course, what has happened? The Washington Post, junk DNA concept debunked by new analysis of the human genome. The vast majority of human DNA seems to be involved in maintaining individuals' well-being, a view radically at odds with what biologists have thought for the past 3 decades. Etc., etc. Typical atheist claims of poor design, and you'll see them all. I mean, they go into inverted retinas, human spine, junk DNA, thymus gland, panda's thumb, human knee joints, prostate glands, wisdom teeth, wingless birds, male nipples, there's a fun one, legless lizards, human appendix, hip bones in whales, and the list goes on and on and on and on. I've actually looked at pretty much every one of them, and there's a very good and rational explanation for them all. I'd be very hesitant to start saying just a couple of points to consider. When we do consider design, just understand that a single feature may not be optimal, but sometimes the combination of that feature with other features makes it optimal. So these guys tend to just look at one little feature, but you need to look at the big picture. All right? Secondly, you need to understand that general vestigial organs are vestiges of ontogeny, not phylogeny. Put that in English. Very often, the organs that you see develop are a process of maturation from being fertilized from an egg to an adult. They're not the result of evolutionary change. All right? All design can only work from the materials that are available. Some organs may not be necessary, but be still nice to have. You'd also need to consider it's unwise to deem organ useless, as the function may be unknown at this time. And we've seen that with appendix, we've seen that with tonsils, we've seen that with many things. We don't know what it does, we'll whip it out. Well, oopsie doodle, we've suddenly discovered actually that's got a function. All right? Some poor biological functions may be the result of loss of information due to the fall. And the Bible teaches that we are decaying as a people, not evolving. We are losing information. Through mutations, we are actually degressing. de-evolving in a sense. And when we look at functions today that seem relatively poor, we need to understand that since the fall, we have, in fact, degraded. So just some thoughts there. I love this quote, and we'll finish with it. Dr. George Wald, a Nobel Prize winner in biology. Listen to what he says, and we'll close with this. There are only two possibilities as to how life arose. One is spontaneous generation arising to evolution. The other is a supernatural creative act of God. There's no third possibility. Spontaneous generation, that life arose from non-living matter, was scientifically disproved 120 years ago by Louis Pasteur and others. And that leaves us with only one possible conclusion, that life arose as a creative act of God. I will not accept that philosophically because I do not want to believe in God. Therefore, I choose to believe in that which I know is scientifically impossible.